Hello, everyone. Welcome to AP Statistics Chapter 12 review. So Chapter 12 was all about regression. We talked about linear regression a bit before, but this is about inferences for linear regression and how to achieve linear regression from other types of regression, like exponential or power. So let's get started. So 12.1 was about inferences for linear regression. So if you're given a linear regression line, what can you tell from that? Now, there's two different types. First is a population regression line, which uses every single point in the population, which is usually hard to get. Just like everywhere else where we usually cannot have the population, we only have the sample. The population regression line is usually written as alpha plus beta x, where alpha is the y-intercept and beta is the slope. And the reason why these are Greek symbols is because they're the population rather than the sample. So the true slope is known as beta, whereas in a sample regression line that only uses a sample instead of the entire population, the slope would be b, and that would be a plus bx, the one we're familiar with. Now, the entire point of this section is given an a plus bx equation, what can we tell about the alpha plus beta x equation, specifically the slope? Given b, what does that tell us about beta? Most of the time it's going to be whether or not beta is zero. And if beta is zero, that means there's no linear relationship. There's no association between the two variables, the explanatory and response variables. So our null hypothesis generally is going to be beta is equal to zero, whereas the alternate is going to either be beta is greater than, less than, or not equal to zero. But that's a bit in the future. First of all, let's talk about the sampling distribution for the slope. This is going to be for b because b is the sample slope. And there's three main things we talk about. The shape, it's going to be approximately normal. The center, we're going to use the mean. And the spread, we're going to use the standard deviation, like usual. Now, what is the mean? The mean mu b is going to be equal to beta because, as usual, it's going to be what the population value is. The standard deviation, though, is a bit more complicated formula. It's going to be equal to the standard deviation divided by the standard deviation of the explanatory variable times the square root of n, where n is the sample size. And it's likely that you're never going to use this formula on the test because we usually aren't given all of these things. Instead, they're just going to give you the standard deviation. They're actually going to give you what's called the standard error, not the standard deviation, but sometimes you get the standard deviation as well, used through the computer output that the questions usually give you. Now, this is going to be what the values for the sampling distribution is, and we're going to use this a little bit. Now, moving on, we can use the sampling distribution to do both a confidence interval and a significance test. And for that, we need conditions. It's always been 3 conditions, but now there's going to be 5 different ones. They are the linear condition, which basically says whether or not the relationship is actually linear. So you can use both the scatter plot and the residual plot for this. If the scatter plot is roughly linear, then this condition is met. If the residual plot does not have a leftover pattern, then this condition is met. And usually if they give you both, you have to say both. Independent, it's not really a graph that tells you this, but you check the 10% condition when sampling without replacement, and otherwise you just make sure that individual observations are independent. Next is the normal condition. So this is a bit different. It's basically that the response variable varies according to a normal distribution when compared to the x variable. So if you have a line, so like that, what it's basically saying is that the dots should be normally distributed. It's a bit hard to draw, of course, but what you can use to determine this is a normal probability plot of the residuals. And usually the question will give it to you. If they want you to check the conditions, they'll give you all of this. You can also use a histogram of the residuals, and that'll give, if that's roughly normal, if it's unimodal and symmetrical, then this condition is also met. After that is equal SD. That's usually from the residual plot. If you have a plot, a residual plot like this with just dots around, and there's really no difference in like the spread for different explanatory values of the explanatory variable, then this condition is met. But if you have something that's like this, and then there's a bunch more spots as the values get higher, then this condition is not met because the standard deviation here is much less than over here. So it's not an equal standard deviation. And your final condition, as always, is going to be the random one, basically saying that the data comes from a random sample or randomized experiment. And the way to remember this is the acronym LINER, LINER, LINER. So now that we have the conditions, you have to check this every time, unless most of the time, actually, it'll say assume that all conditions are met, in which case you don't have to check the conditions. But be ready to check the conditions if they ask you to. They'll generally give you all the information you need to actually check the conditions. Okay, moving on. So degrees of freedom, it's going to be a bit different. Earlier, we had n-1 for most cases. Then last unit, we had chi-squared, where it was number of, well, it was also n-1 for one way, but for two way, it's rows -1 times columns -1. And now we're going to get a different formula. It's going to be n-2. And that, we don't really know why that's the case. That's beyond the scope of this class. But the formula is that we're going to use n-2 as our degrees of freedom. So if we had a sample of 50 students, your degrees of freedom would be 48. So the standard error formula. So we know that the standard deviation formula is going to be equal to the so the standard deviation of B is going to be the standard deviation times this over the square standard deviation of the explanatory variable times the square root of n. For standard error, though, the formula is going to be a bit different. Since we're not going to be given these actual population standard deviations, we're going to have to use sample standard deviations. That's going to be S over S sub x, and then this time times square root of n-1. Again, we don't know why that's the case. That's just a formula. And like I said, you're probably not going to have to use this formula ever. They're generally going to give you the standard error. That's one of the parts of the computer output, which I'll show you later. But generally, when you have the computer output, it has all the values for the constant, which is just a, and then all the values for the slope, which is b. And you have the actual value. You have what's known as the standard error. You have t, and you have p. So all we're going to be looking at is the b value right here. You might use the a value when it's asking you to find the actual equation for regression, where you actually use the values of this. So this you might need, this you might need. For standard error, all you care about is b. That's the value we find using this formula. You're probably never going to use that formula. T and P are for significance tests, and we'll get to that later, but you might use these two values too when you're doing significance tests. Okay, so let's actually get into the t interval for this slope. The formula for this is b plus or minus t star times the standard error of b. So we know how to find b. They give it to us. That's the value of the sample slope. We know the standard error, that either use the formula, which you probably will never do, or use the computer output, which is much more likely. And we know how to use calculate t star from previous units. That's just inverse t, and then you do the area that's to the left. Instead of just 95%, you do 97.5. Remember that little caveat over there. And then you also plug in degrees of freedom and you get t star. That's the critical t value. And then now you have the formula. So it's not really anything special. More often than not, you're not going to use any special function on your calculator to do this. You're just going to write this formula, calculate the necessary values, and then write your answer. Most of the work is going to be done with your intro sentence, your conditions, and then your concluding sentence and interpretation. There's barely any work for this because it's just this simple formula. You're given most of the values. You just have to calculate t star and then plug it in. So that's for the t interval. And remember, this is a t interval, not a z interval. The reason why is because we don't know the actual value, so it's standard error, not standard deviation. So the next thing we can do is a significance test. And for that, we need something called a t statistic. Again, you might remember that from before. The t statistic is going to be equal to b minus beta naught, and beta naught is just your null hypothesis beta. Usually is going to be 0, but just in case. And then over the standard error of b. And once you have this, you can do TCDF with a number of degrees of freedom and calculate the probability value. Now, there is one more thing though, and that's with the computer output. Remember when I said we had T and P that we're not going to use except in significance tests? That's where we do. So now that we've introduced significance test, a t-test for slope, what you're going to do is the intrasentence, the null and alternative hypothesis, the conditions and everything, and then you calculate the t value using the formula that I just showed you. T is equal to b minus beta naught over standard error of b. And then you double check that with the t value they give you on the table. You have T and P. Just you check those for the B value, and that's actually the T statistic is this one, and the actual probability value. So you can use TCDF or you can use this. It's probably better to show work that you actually know what you're doing instead of just copying from the computer output. Now, one little thing, this P value they give you is for the alternative hypothesis beta is not equal to 0, or beta is not equal to whatever the hypothesized value is. So if you're only doing a one-sided test, it's going to be divided by 2. And that's basically it for 12.1 because it's not really that much anything new. It's just you have to do this with linear regression rather than just samples. 12.2 is about transforming other equations to achieve linearity. So you're going to get other types of equations, mostly power and exponential, and you're going to turn them into linear equations to do regression. So there's a few transformations you can do. You can either transform x or transform y. So let's say you're given the equation y equals ax squared, just an example. Let's say x is going to be the size of the hole and y is going to be the amount of Cheerios that can fit in it. That is one of the example problems, by the way. This is related to the area that's in the hole. So it's going to be related to x squared. So that's why this is the example. So if you want to transform x to get a linear equation, you're going to have y as the response variable and x squared as the explanatory variable. And now this is proportional to x squared. Before, y is not proportional to x because of this square. So that wouldn't be linear. But if you plot actually x squared versus y, you're going to get approximately a linear equation. And now you can also transform y. You basically do the opposite. You take square root of y, and that's going to be proportional to x. So now you can plot x and square root of y, and you're going to get approximately a linear equation. And you can do it either way. Both ways get you the same result. Not the same equation, of course, but the same values when you plug in different values. So that's if you know what the equation is going to be. If you know it's squared or cubed or square root or anything. What if you don't know? That's where logarithms come in. And there's two main things that you can use, power and exponential, that you can use logarithms for. So power it's a times x to the power of b is power, and exponential is a times b to the power of x. So those are the main two things we use logarithms for, and there's two different results that we get. So an example of power would be the x squared that I showed you. Example of exponential would be like 2 times 3 to the power of x. And that is actually harder to transform because you can't use any of these normal transformations. You would have to use logarithms either way. So how do you use logarithms? So there's two cases. For power models, you would take the ln or log. Either one works. Just make sure you're consistent each time. The natural logarithm is just base e. So you can do natural logarithm base 10, base 2, whatever. Normally people do natural logarithm or base 10, and you can choose whichever one. I'm just going to use natural logarithm here. So this is going to be ln of y versus ln of x, and that's going to give you a power. The reason why is because if y is equal to a times x to the power of b, and you take the ln of both sides, you get ln of y is equal to ln of a times x to the power of b. The product rule for logarithm says that this is equal to ln of a plus ln of x to the power b. And the product, the power rule for logarithms says that this is going to be equal to ln of a plus, you bring down the power here, so it's going to be b times ln of x. And now what you're going to get is a function or an equation that's ln of y is directly proportional to ln of x with this additional slope, y-intercept, and the slope is just going to be the power. So when you get an equation, when after you transform it here, the slope that you get for this is going to be the power that it was originally. So if you don't know what power is going to be, an easy way to do that is use logarithms and find the slope. That's just going to be the power. So now that's for power models. For exponential, it's going to be similar. It's going to be ln of y versus just x, not ln of x. The reason why this works, let's have y is equal to a times b to the power of x. You take ln of both sides, you get ln y is equal to ln of a times b to the power of x. So now you have ln of y is equal to, same product rule says this is going to be ln of a plus ln of b to the power of x. And now we can do the same thing with the power rule, bring down the exponent. This time the actual exponent is the variable. So you're going to have ln of y is equal to ln of a plus, and then you bring it down x times ln of b. So if you rearrange it a bit, this ln of b is just going to be the slope for x, and now you just have ln of y on one side and x on the other. Not ln of x, just x. That's why it's ln of y versus x. So ln of a, again, is going to be the y-intercept. The slope this time is going to be the natural logarithm, or whatever logarithm you used, of the base of the exponent. And the reason why I'm showing you this is so that in case you forget, you can derive it on the spot and remember which one it is. I always prefer derivations to actually just memorizing stuff. So hopefully this works for you too. All right. So that was basically transformations to achieve linearity. And it's time for an example. And this time I'm also going to include an MCQ since we're getting closer to the AP exam, and there's a lot of MCQ questions on the AP exam. So this one, it says the relationship between the explanatory and response variables is modeled by y equals 2.7 times 0.316 to the power of x. Which of the following scatter plots would be approximately linear? So this is, first take a moment to pause and answer. Okay, so how would we solve this? Let's look at this equation. It is an exponential because it's 0.316 to the power of x. That's an exponential model. So what did we just learn about logarithms? We said that for an exponential model, the linear, to transform it into a linear equation, it's going to be ln of y or log of y versus x. We need to find that option here. Y against x, no, that's just going to be exponential. Y against log of x, that's nothing. That won't make anything linear. Log of y against x, that looks right. Let's just check the others though. Log y against log x, that would be for a power model, which this is not. And a plot of y against x to the power of 0.316. So that's actually a bit tricky. If it was 0.316 to the power of x, then it would be linear. Obviously, you wouldn't know that, so it's not a preferable method. You would never know that 0.316 is the base. So you would use log y against x. But if you somehow knew it, you could do it. This is x to the power of 0.316 though. So that wouldn't work. That is just a power model while this is exponential. So the basics, that doesn't even work. So the answer would be C, log y against x. And then we have an FRQ question. So this is going to be about inferences. So there's a long explanation about this. The important thing is that 16 tires, so that our sample size is going to be 16. And we have explanatory variable is distance calculated using the weight of a tire, and distance calculated using the grooves of a tire. So that's the explanatory, that's the response, and this is the scatter plot that it gives us. Here's the Minitab output. It says assuming conditions are met, so we don't have to actually check the conditions. It's good practice too, though. This doesn't give us all the information. That's why I had to say assuming all conditions are met, because I couldn't fit all 4 graphs on this screen. So you could try and check it. Obviously, you can't with this because it doesn't give you the actual data. But when you do other problems, make sure you always do the conditions. It says construct and interpret a 99% confidence interval for the slope of the population regression. All right. So I'm going to go to the next slide. The Minitab output and the graph will still be there, but it's just more space for us to work. So we start with our general statement. We want to estimate beta, the true slope of the regression least squares regression line, relating the distance calculated using the groove method to the distance calculated using the weight method. Um, uh, and that would be your intro statement. And then since all conditions are met, if they didn't tell us that all conditions were met, we would say if conditions are met. But since they do tell us it's since conditions are met, we will construct a 99% t interval for slope. And that would be your intro statement. I'm not writing all that down since I have to draw it and it takes a lot of time, but just make sure you always write that down on the paper. Now, to actually do the work, we don't have to do the conditions since all conditions are met, but we actually have to do the work. So this is a confidence interval, and the formula for that is b plus or minus t star times the standard error of b. Let's see. What is b? That's going to be 0.79021. Plus or minus t star, let's figure that out later. But before, do we know standard error of b? That is going to be this right here. That would be 0.07104. I think the point here is a bit is missing, but it should be 0.07104. So now what is T star? We use T inverse T for this. So you go to stats, distributions, and inverse T. What is our area? Well, we know it's 99%, so it's going to be 0.995. Remember, we have to add that little extra thing because we're taking everything to the left. Of course, if you have the center option, you can do that in 0.99, but this just works for everyone. For degrees of freedom, there were 16 tires, so it's going to be 16 minus 2, which is 14. You plug that in, and you get 2.977 approximately. And now you just plug all this in. 0.79021 minus 2.977 times 0.07104. And that's the formula, right? And we have 0.5787. And then you have to do the same thing, but with plus instead of minus. So you can just copy the output from that and just do plus instead of minus, and you get 1.0017. So that's our confidence interval, and you can go ahead and box that. And now we just have to interpret it because it's said to construct and interpret. So that just means we are 99% confident that the interval from 0.5787 to 1.0017 captures the true slope of the least squares regression line relating the calculated distance using the groove method and the calculated distance using the weight method. Now, what does this mean? This means that there is a linear relationship between these two variables because 0 is not found in this interval. So it's kind of like what we did before. If 0 was found in the interval, that means that there is no convincing evidence of a difference. Here, since 0 is not found in the interval, that means it's implausible that it's just a horizontal line, meaning it we have convincing evidence of a linear relationship between these two variables. So that's our answer. We could also do a significance test on this just to be safe. In fact, if you look at the p-value, it's close to 0, which means we do reject the null hypothesis, and there is convincing evidence of our alternate hypothesis. But since it didn't ask us for a significance test, we don't do that here. We just do a confidence interval and interpret it. So that's it for this video. It was relatively short because chapter 12 isn't that long of a chapter, just 2 sections. First, we covered significance tests and confidence intervals for linear regression to find the slope. And then we did transformations of other equations into linear equations to do calculations. So that's it for chapter 12, and that's actually the last chapter of AP Statistics. So there will be AP prep videos as well coming out, but yeah, good luck on the AP test.